Howdy, everybody. Here for day 19 of Advent of Code. I've been having a lot of fun. I hope as you guys have been solving the problems, you've been having fun as well. And hopefully my analysis can, prove useful. I've gotten a lot of positive feedback and even some help. In fact, the first thing I'd like to talk about is some stuff that I missed in day 17 just because of some refactoring I did. But again, I appreciate all your feedback and everyone being a part of this and watching my videos and subscribing. That's awesome. Thank you guys all for doing that. Um, and let's just get started. Yeah, so day 17, I'm back here looking at the day 17 code. When I described the problem on my analysis, I did okay, but I actually missed some code that I wasn't paying attention to when I was doing some refactoring. So if you remember, this is a Dijkstra's algorithm. You're trying to find the shortest path, but there were some constraints on it. And in particular, one of the constraints was you can't go in reverse. And so when I was doing the refactoring, I created these neighbor functions right here, neighbors P2 and neighbors, that were meant to like help you find the next neighbor. Well, obviously one of those is you couldn't go in reverse, and I didn't include that in my refactor. So I've updated the code in that day's gist, so you should be able to see it. But here's just the thing, right? Is the only thing that changes is I also do a check and say, hey, am I going in the opposite direction? And then if I am, I can't add that to my neighbor set. And then for part two, I had to do the same thing, but you also obviously can't reach an end point if you haven't gone at least 4 tiles in that same direction, right? That wouldn't be a valid path. If you'd only gotten 3 and got there, it wouldn't count. And so in the Dijkstra algorithm, the way that I had originally written it, I just put the neighbor and the goal function inside the code and modify it. In this case, when I refactored it, I wanted to make it more generic so you could see that like the Dijkstra algorithm was just generic and you really just needed a goal and a neighbor. And that's where I missed that. So what I do now in the change, besides passing a neighbor function, I also pass a goal function. So the goal isn't just a point. The goal is some kind of function that will tell you if you've reached the goal. And so I just check there and I say, hey, does my goal function succeed? And if it does, I know I'm done. And then down here in the main, when I pass those goal functions, for the first part, there's nothing other than am I at that point that I'm done. But for the second part, I need to say, hey, am I at the goal position and have I traveled in my current direction 4 or more times? So that's what you get there. And that's kind of, those were the changes that I had to make, I guess I had to say. So thanks for pointing those out. Again, you probably have done this too, as I have. You get to a solution and you get it working, you solve the problem, but you don't want people to see your ugly code, so you spend some time refactoring. That's what I try and do. And so and sometimes unfortunately you miss it, especially on these cases. I'm a pretty big fan of unit tests, maybe not to the extent of, oh, you have to have every single line covered in every single case that ever existed, but I am a fan of unit tests. And so unit tests would have caught something like this. And so I don't usually do unit tests when I'm doing Advent of Code unless there's something I want to be very careful about, but or something I'm not sure about and want to like check. But that is a good example of a time when unit tests would have been good, right? If I had unit tests on all my things and was updating them as I went, I would have caught these issues that I had missed. But again, thank you for your input. Thank you for finding those and catching them. I'm always happy to, make things better and make sure you guys understand the problems. And I have gotten a lot of good feedback that generally it's readable. And part of that is because I spend time refactoring the code, right? Making sure it's readable, understandable, making sure the flow works. And it's not perfect. There's always ways to improve. But just like when you're writing a research paper or anything, you never submit your first draft unless you're late and it's midnight, right? But you want to finish it, get it working, make some changes to it, get some insight, try and fix some things, look for simplifications, right? Until you get to like the perfect quote unquote paper, and you want to do the same thing with code. Okay, so given all that, let's get to day 19. So what is day 19? You are now at the parts factory where they're machining parts, but because now that everything's running, there's suddenly a relentless avalanche of machine parts. It's a bunch of parts, and they need to check whether each part is within some tolerances, right? So you're going to be given, each part is going to have 4 values, and your job is to test the part given a list of conditions to determine if the part should be accepted or rejected. And here's what the rules look like. They look pretty complex, but the way you can think about it is the rule is given a name, and then you're given a condition, and then if that condition is true, you're given either a new rule to check, or I guess a new workflow. These are called workflows. You're given a new workflow to check if the condition is met. Otherwise, you keep trying conditions, right? So if this condition isn't met, then you try this one. And the last condition, it says, is always just like a destination. So you're either going to a new rule. So it's kind of like, think of your else statement, right? You're essentially asking, if A is less than 2006, go here. Else if M is greater than 2090, go here, A being accepted. Otherwise, or else, go here. And so there's different, and that's kind of what this part is describing up here, right? It says EX is the name, these are the rules, and there's an otherwise rule. And the rules could either be go to a new workflow, right? So 1 means go to another workflow. 2 mean go to another workflow named 1. 2 means go to another workflow named 2. R is rejected and A is accepted. So the way to think about it is you're kind of going to build up this kind of like tree of rules, and I just store them in a hash map. But you're going to start it in. It says the start position is in, and you're just going to start evaluating rules kind of recursively, right? Not really recursively, but you're going to evaluate a rule, and it's going to either give you an accept, a reject, or some new workflow that you need to go to, right? So this one says if S is less than 1351, go to PX. So you'll go here, and it will say, hey, if A is less than 2000, go to QKQ. And so if that's true, you go to QKQ, and then you check, and it says, oh, if X is less than 1416, go to A, or A meaning A is accepted, so you can stop there, right? So I actually drew the example. This is not the full example, and sorry if it's hard to describe, but again, you can think of it as a tree, right? You have your in right here. Maybe I can just highlight this. You have your in right here, right? And you're going to do a check. There's some kind of condition, right? And you're going to say, hey, if S is less than 1351, then I want to go down this path. And that's going to lead you to PX. And so I drew this out mostly for part 2, but I do think it helps to visualize it, right? Is if you think what you're doing, you're going to kind of create this tree that is eventually going to end on either accepted or rejected nodes. And that's all you do for part 1. So you can see you're going to give a list of the instructions. That's you kind of building up the tree. And then you're going to be given a list of parts, and that's going to give you your X, M, A, and S values that you're going to use to do those comparisons. And then these values are going to be used to help you traverse the tree, right? So you're going to be able to go through the tree from here to here, here to here, here to here, and eventually say, oh, this one's rejected because it met the conditions in such a way that it fell to this position. Again, this tree is not complete for the test input, so if you see it and think I missed a spot, it's very possible I did. I was doing this for part 2 to try and visualize it, which we'll talk about for a second, but it helped me visualize kind of creating a structure of parents that you'll need for part 2. So anyway, you can see the actual input is substantially larger, but the code itself is not tough once you understand, oh, I'm kind of building a tree, and in this case I used a hash map to store like the name and the conditions that are associated with it. And then you just iterate over your list of parts and determine what they are, right? So you can kind of see how that works for part 1. If I go to the main function, what's going on here? Oh, I got my fingers in the wrong place. So if I go to the main function and go to part 1, you can kind of see what I do is I create a list of workflows, and I put them in a hash map, right? So I know the window or the workflow name and the actual workflow object. I can look it up. So whenever I get to, go to this window, I can just look it up in this hash map. And that's just separated by a list of new lines. And then the rest of them are the parts that I need to parse as well. So once I have those parts, then I can just process each of them in part 1. You can see here, I just filter them by the ones that are accepted when they go through the process. And then I sum up their total rating. And it describes what the total rating is here in the thing. It says, okay, for all the ones that are accepted, the total rating is the adding up the X, M, A, and S values. And then it asks you, what is the sum of all those, right? So that's what I'm doing here, right? I have some function to do the total rating that's going to be summed up, and I'm going to filter by all of the workflows who are accepted. So what do those data structures look like in that function? Obviously, we have to do some parsing. I chose num in this case. I feel like I'm getting more comfortable. The first thing we're kind of interested in is a destination. I guess I should have done spell check on my stuff. And the idea is the destination is either going to be accept, reject, or a pointer to some other workflow, right? And so we want to store the string there. In this case, I didn't use lifetimes because this destination, I don't remember why I didn't. You could potentially still use lifetimes here. I think there was some string thing that made it easier to do it, but anyway, back on topic. We want to know a destination, right? So that's in the code, that is like these parts right here, right? It's going to be this or this or this. Those are the destinations. And so this is going to be to another workflow. This is going to be accept. This is going to be reject. We want to be able to parse those, and that's what this function does. I just look for an A, R, or some kind of alphanumeric, and if I find any of those, I return their corresponding destination enumeration. Then we also want a condition, right? You can think about it in the system as like this part right here. We have a whole rule, which is this part, but for now, and I'll show you the rule in a second, we're really just interested in this part right here, right? And so there's going to be some kind of value. There's going to be a less than or greater than, there's going to be some kind of letter. It's going to be X, M, A, or S. Then there's going to be a less than or greater than, and then there's going to be some kind of digit, right? And so that's what this condition parser does. And I want to do an enumeration because I want to know if I'm doing less than or greater than. The less than or equal and greater than or equal are actually only useful for part 2. If you look at the conditions, these are the two that only happen like in the actual input, but these will be useful in part 2, and we'll talk about those in a second. Same thing with part 2. I have this opposite function that will give you the reverse corollary, right? Like if it's X is less than 300, the opposite of that would be greater than or equal to 300, right? So I create this opposite function for part 2, which we'll talk about a little bit more. Then I create an evaluate function for it. And the idea here is we want to be able to, given a part, we want to evaluate if that condition is true, right? And so I'm just using the match logic here where I say, hey, if it's less than, and the condition actually works, right? So the part's value for that variable is less than the value that I have, then I return true. And I just do the same thing for greater than, less than, equal, and greater than equal. Again, I don't think these two parts are necessary for part 1. It's just these two. But all this is doing is actually evaluating the thing, right? We say, oh, if I get a less than, and my less than evaluates to true, like I actually do the check, right? If it was like M is less than 200, this would say, hey, is the parts M less than 200, and if it is, then I return true. So I just go through all those, and any of them that don't evaluate to true or any other values just return false, right? And so that's a pretty simple evaluate function, right? Then we need to parse it. So what does it look like parsing wise? Obviously, we're going to look for one of the x, m, a, or s values, right? So the left-hand side, if you look at the example, the left-hand side is always one of those. And then we want the less than or greater than sign, which is this part right here. And then we want the alphanumeric, the digit, which is right here. And so we just get those, we turn the value to an integer, and then based on the less than or greater than that we get, we create the corresponding condition, right? Less than or greater than. Again, you can see I put unreachable here because we would not get the other two. They'll be useful in part 2, but we wouldn't get them, so I didn't try and like parse them in the parser. Okay, so we've talked about the direction, which is this part, and we've talked about the condition, which is this part, and so now we can do a list of rules, which is this part right here, right? So we basically just combine these two to generate our rules. So what does the parse look like for that? Again, we're either going to parse a condition and followed by a colon followed by a destination. So we're either going to get something like this, or we're going to get something like this, right? And so that's this part is the destination, or we're going to get some destination, which is just a string. And so I do an alt here for parsing the actual rule, right? So the rule is either an evaluation or a fall through, and it's going to be one of those two, right? If it's an evaluation, I'm going to do this. I'm going to parse a condition, a colon, and then a destination. Otherwise, it's going to be a fall through, so I'm going to create a fall through with the destination parse. And those are the two rules we're interested in, right? They're always going to evaluate from top down, right? So you'll either do an evaluation or you'll do a fall through, but it'll usually be like evaluation, 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 fall through. And so that's what the evaluate function looks like for our rule. I realize the naming convention now may be a little bit funny, but when we're evaluating a rule, if it's a fall through, that's a very simple case, right? If we get a fall through, if we get to this point right here, we know that we're just going to go to that destination, whatever it is, right? So we can just return that. If it's an evaluation, right? So if we're evaluating this piece right here, now we need to do some checking, right? So we pull out the condition and the destination, and we see if that condition evaluates to true, right? And if it does, then we return the destination. Otherwise, we return none. And we'll talk a minute why we return this option or none. Most of it has to do with the fall through nature of it. Consider essentially what you're doing. Think about when you're evaluating a workflow. It's one big if-else statement, right? So you're going to try and evaluate this to true. You're going to try and evaluate this to true. And if none of those work, you're going to evaluate this one. So to put it, one way to easily do that is called a map find function, where you just find the first value that evaluates to true in your list. So imagine I'm going to have a list here. I can call this map operation, this map find operation, and the first one that returns true, or returns some value, I should say, is the value that you get. And we know we'll always get a value because the last one is the else. So I can show you what that looks like, and that's in the workflow part, right? Before we get there, really quick though, how do we parse a workflow? Well, we know it's got a name, and then we know it's got an open bracket, and then it's just a separated list of rules that we parse, and then an end bracket, and that will create our workflow, right? Okay, now to that evaluate. Again, because I set up the previous evaluate to return an option direction, I can just call this map find function. And I think this was a cool thing. The reason why I'm mentioning it is I haven't found a use for it yet, and this seemed to be a really good use for it, right? You've got a list, and you're going to evaluate a list of rules. You're going to evaluate them in order, and you're going to stop at the first one that evaluates to true, right? So you call this find map, and it's going to return the first one where evaluate returns some value, and it's going to give you that value, which is the destination, right? So again, just to reiterate, we have an evaluation function on the workflow that's that's going to iterate through all of its rules and find the first rule that evaluates to some value, and then it's going to return that value, which is the destination. Well, how do you do that evaluation by rule? Obviously, if it's a fall through, you've reached the end, and you can just return that destination. So you're going to return some value. Otherwise, you're going to get an evaluation, and you want to evaluate that condition. And if it's true, you're going to return some value. Otherwise, you're going to return false, right? And then how do you evaluate a condition to determine which of those are true? You just actually do the conditional check, right? If it's less than, you check if the given value in the part is less than the expected value, and if it is, you return true. And you do that through all your expressions, and if one of them, if it fails, otherwise you're going to return false, right? I hope I said that right. Okay, so what is all this? So I have 3 evaluation functions, and I'm evaluating like each piece in for its own part, or for its own enum, or for its own struct. And the reason why I like this is because we can think about this in like smaller pieces, right? Sometimes code is much easier to understand and get to a solution if you can think at just one piece at a time. So that was really helpful in solving this problem. Is I always just thought from a top-down approach, right? When I was doing the workflow, I was like, hey, if I can just evaluate a bunch of rules and have them return a destination if they're correct, then it's as simple as this. And then when I was looking at the rules, I said, oh, if I can check a rules evaluation, and if it's correct, I can return some destination, or if it's not, I bail. Or if it's a fall through, I just return the destination. Then that's a real simple way just to evaluate the rule, right? And so now I just need to worry about how do I implement this condition evaluate? Well, that's as simple as just checking the pieces, right? Again, if you're doing speed coding or trying to solve the problem very quickly, you may not get to this. But if you have time to think about it, that top-down approach of, oh, I don't have to solve every problem right now. I'm just going to assume there's a function called rule evaluate, and I'm going to use that for my workflow evaluate. And when you're building the rule evaluate, you can say, oh, I'm not going to worry right now about the condition evaluate. I'm just going to worry about how do I solve this part of the problem, and then I can come to doing that. And that's helped me a lot in solving these type of problems, right? If I think about it just in the scope of what I'm working on, I can focus on, oh, I need to write this function to do this thing a little bit later. Okay, that was a little side way of me saying, essentially what happens is I'm going to have this tree, and I'm just going to traverse it, right? I'm going to check which one evaluates to true, and the first one that does, I'm going to follow that path, and eventually I'm going to get an accepted or a rejected. And so that's what my code looks like for part 1. And you can see what I do for part 1. Then it's just as simple. I've done all the work of building up piece by piece. Now I can just say, hey, for part 1, I'm just going to filter by each part that process is accepted, and then I'm going to map it to their total rating and count their sum. Oh, I don't think I showed you the parts one, right? What does that look like? It's not much more complicated. Here's me parsing the part. At first, it looked like JavaScript or JSON, and so I almost used Saturday to do it, but I realized that wouldn't work. So I just used nom. What does that look like really quick? It happened to always be in order, so you can literally just say like, hey, pull this tag, and then the next is the X, pull this tag, the next is the M, so on and so forth. But I did create some helper functions for the part. That's the total rating is just the sum of each of the values. And then I had this set function that, you know, the conditions are going to get a character, but I want to like set that thing. You could potentially use like a hash map or something like that, some kind of data structure to do that. I just use these set and value functions to help me either get the value or set the value based on the character, and you just do that in Rust with the match expression. Okay, but what does the process look like? The actual process, right, is now you've got a part, and we've spent all the time building up from a direction, a condition, a rule, a workflow. Now we have all of those, and so this is all the code you need to do now for processing a a part, right? So what do? You start it in, right? That's what the problem says. Um, right here, you start it in. So we're going to start there. And we're just going to loop until we either get an accept or reject. And what does the loop look like? We evaluate the part based on our current thing, which starts at in, right? So we're going to evaluate in, and if it's accepted, we accept. If it's rejected, we reject. Otherwise, we're going to get a workflow to go to, right? It's going to tell us some new direction. And what is that direction? And so we just set our cur, right, the current workflow we're working on, to the next one in the hash map, right? So we look it up in the hash map, and now we know the next one. So now when we loop again, we're a little bit deeper, and we can just do that evaluate function again, and we're going to keep going through the tree, right? We're going to just keep going through the tree, right? So if S is less than 1351, cur will now be PX, right? And then if A is less than 2006, our cur will then be QKQ, and then if X is less than 1416, it'll evaluate to accept, and so we can accept that part. We can mark it as accepted. And that's the loop for the process. So again, that's all you do for part one. So that was, again, I hope you recognize that we kind of built up piece by piece, right? We had destinations, we had conditions, we have rules that map conditions to destinations, and then we have workflows that are a list of that are a list of those rules that end in some fall through thing, right? And so doing those evaluations then becomes, just as easy as just checking all of those things. Okay, this is part two. Sorry, I'm there. That'll be a little confusing. But that's it for part one. And if you run it, this is the answer I get for part one. I did double check it this time to make sure that I hadn't missed anything. Although if I have missed anything, let me know. I could have missed something. So what changes in part two? What they say is the processing still isn't going fast enough. And so they have a new plan. Rather than sort the parts individually, they want you to figure out the ranges of parts, maybe is the way to think about it, that will be accepted or rejected. So each of the 4 ratings has an integer value of 1 to 4,000. And they want you to calculate all the distinct values and figure out if they're accepted or rejected. So now instead of having a list of maybe hundreds of individual parts you might have to evaluate, you now have trillions, right? You have like 4,000 times 4,000 to the 4. Well, I don't know exactly what that is. It's what is that for? 640 trillion, 6.4 quadrillion. It's some huge number, right? And just like all the previous days, when you see a ginormous number like that, you have to say to yourself, there's got to be some other solution, right? I can't iterate, right? This tree that I've made is just for the test input, right? The tree that is created by the actual input is substantially larger and goes substantially more directions. Or I should say it fans out substantially more. So there's a lot more for you to check. And to check that a quadrillion or even a trillion times is just not feasible, right? You have to say to yourself, I can't do that. So, because think about what you're going to do. You're going to start at X, M, A, S all being 1, and then you'd set S to 2, and you try it, and you'd go all the way to 4,000 and try all 4 of those 1,000. Then you'd increment A to 2 and start S over again, right? And you're slowly doing all of those, right? So you have some huge number. And so they want you to know how many of all of that set of values, 4,000 to the 4th, are like valid, would produce an accepted. And so you just can't check all of those, right? You're going to get some huge number like this. This is the number of accepted, right? And there's going to be some number of them that are rejected. So you're going to do on the order of double these depending on the input size, right? So how did I come to solve this problem? Well, I actually graphed it out. This is why you see me having these numbers. I started to think to myself, like, is there some way to like kind of track the known values, like the known valid values of X or S or MAS? And so I started tracking these. You can see these little blue ones are the ones that I was tracking, where I would say like, okay, well, at this condition right here along this far right side, these are all the first values, or like the first conditions, the way to think about it. Along those first conditions, I know that S must be less than 1351, A must be less than 2006, and X may be less than 1416. So that's actually helpful if you think about it. Given those conditions, I know that M can be 4,000, any of the 4,000 values, but X, A, and S all have to be less than these values, right? So there's now like a subset. And you can actually calculate this, right? If you know that, I probably don't need to write this out, but if you know that S is between 1 and 1351, and A is between 1 and 2006, inclusive, I should say, and X is between 1 and 1416, and M is between 1 and 4,000, you actually know how many parts fit this criteria, right? It's just multiplying these 4 together. It's the product of these things, right? So that's some huge number, but you now know, you now have like this path right here. You know exactly how many values this path accounts for in the total number of accepted parts. That's this right here, right? So the question then becomes is, well, if I can calculate this path, can I calculate all the other paths to the accepted values? And it turns out you can, right? Think about how you got here to accepted. You had a list of parents and their conditions, right? So you know that starting here to get to this accepted, I have to be in this, I have to have met this condition, and this condition, right? So you can think about it as like you have a list of conditions that have to be met in order for you to, in order for those parts to be accepted. And then once you've done that, you can do the math over here to figure out the total. There's just some gotchas now that you have to figure out. Well, how do I get to like this accepted value, right? This part is still the same. This part is still the same, but this part is not, right? If you look at QKQ, what does it look like in this solution? QKQ says if it's less than 1416, return accepted. Otherwise, go to CRN, right? And so that's what I'm doing right here. How do you think about this? So you have to ask yourself, how would I get to this path, right? And the only way you would actually get to that path is if X is greater than or equal to a 1416, right? You already checked that it was less than, and that did not pass. So you know that going this way, you actually, the value of X actually has to be the opposite of it. And remember, I had mentioned to you before I wrote that opposite function. That's the reason for that, right? So if That's the reason for this opposite function and the less than or equal to and greater than or equal, because if my value is less than 1416, I know that my value, anything that goes down this path, has to be greater than or equal to 1416. And then I just do the same logic, right? Now I'm at CRN. I know that X has to be greater than 2662. Is that the value? I don't remember if that's what it actually was. Yeah, greater than 2662. So now I have a path to this accepted route, right? I know that these values get accepted when S is less than 1350, A is less than 2006, X is greater than or equal to 1416, and X is greater than 2662. So so the way to think about this is, if I ever, obviously this left path is really easy because always the first evaluate to true. But if I ever do a rule that evaluates to false, the previous rules I just have to apply the opposite to those as well. And that's what gets me down this path. So let's look at one more that's slightly more complicated. Notably here, right, because there's multiple rules that you can go down. And the reason I just want to describe this is because think about a path that if QKQ was slightly different and it had another rule here, we'll go down a little bit further, but it said like this rule said, instead of it just being otherwise go to this rule, it had another rule over here. And this rule said something like, well, let's just do it in one of the ones where it will actually work, right? Maybe there isn't actually a good one to show. Oh, it's this RFY one is a good one, right? So I didn't trace the whole path, but let's actually look at the path that ends with this accepted unit right here, right? So we know that in order to get there, you can kind of follow it way up. We know that in order to get there, we start at N and we have S less than 1356. We know that these rules have these two have evaluated to false. We've already checked those paths and they're not going. So the default is to go down this path. So what does that mean? It means that to get here, you'd have to have a value of A greater than or equal to 2006. And you would have to have a value where M is less than 2090, less than or equal to 2090, right? So you can't have gone down this path. You can't have gone down this path. And this is the fall through. So in order to get there, you would have had to, you want to have done the opposite of these, right? This path, maybe the better way to say it, is the equivalent to the opposite of all of the previous paths that are in this same rule set. So you'd only get down here if all of those had failed. And the same thing down here, this RFY, even though I don't have the values here, in order to get to this A right here, I would have had to fail on this one and fail on this one and then fall through to this one. So this one would have to succeed on the opposite of this and the opposite of this. So when you're thinking about this set right here, the equivalent of this, what is that for this? It is this path. The opposite of this path and this path will get you here. And then it's the opposite of this path and this path, which will get you here. So I hope I've made that clear. Like, in order to get here, the conditions you have to meet are this one, the opposite of this one, the opposite of this one, the opposite of this one, and the opposite of this one will put you here. And so once you've done that, though, you can just do the same math here. All you're doing now is just changing the mins and max based on these values, right? You now know what you have to do to get there. So you can just apply all of those logics and the logics opposites of the rules you didn't go down to get to the place where you need to go. So what does that look like in code? It turns out not to be as difficult, right? If I didn't explain it well, I'm sorry. But essentially all you're doing is you're looking for you're trying to generate a list of accepted paths, right? So again, you're building up this thing right here, or this, this stuff right here to get to over here, so those lists of paths include all of the conditions or the opposite conditions that would get you to this point. So that's what this generate accepted paths does. You're going to give a workflow, you're going to start it in, you're going to have no parents at the beginning, but you're slowly going to create a list of accepted paths. And then once you have those paths, you just can calculate the combinations to get the size, right? And so I'll show you what those two functions look like. First, the generate accepted paths. It's happening again. There we go. Okay, so how does generate accepted paths work? Obviously, you need the workflows because you need to be able to go through your tree, and you need your current position, right? Like, where are you at in the path? We started in, but as we're traversing, we could be here or here or here or wherever, right? You'll be somewhere in the path. And then we need a list of parents, right? Who have I visited to get here before? And again, so like, if you're right here, your parent would just be right here. If you're like right here, your parent would be here, the opposite of here, and the opposite of here. Those are the things that got you here. That's the way to think about the parent, right? Is like, you're now at a position, what are like the conditions previously that got you to that position? And then from that, we can just generate a list of paths, right? So what does that look like? And this is a recursive function, right? We're going to keep calling it repeatedly. But how do we do that? We're going to start with a list of paths. So this is going to be the list of paths that we're going to generate from our current position, right? And wherever that is in the map. And we're going to get the workflow that we're on, right? So you can think about that as like this position right here. We're going to get that position we're on. We also want to track our previous conditions, right? So this is what I mentioned. If we're evaluating right here, the rules, we'll want to have known the opposites of the ones that we've evaluated before, right? So that's what we're tracking there. But then we just go through each of the rules. And most of this is, again, comments and stuff, but it's actually not that hard to think about, or it's not a lot of code to go over, right? Obviously, for each rule, we want to create a new parent that we're going to use, and that's just our current parents list. Plus, we're going to extend our previous conditions, right? So when we start at the top, we're going to have no parents and no previous conditions, and it's going to be 0. But when we're like, for example, when we're on this rule, we're going to have like, this is our parent, and these is our previous conditions, which are the opposites. And so we want to be able to like have that list, that kind of chunk right here that we can reuse, right? And then we just do a match on the rule. If it's an evaluation, we know that we need to go further down that path, right? So we're going to add that evaluation to our new parents. And then we're going to push the opposite on our previous conditions, right? So think about it, is when you're building this first rule, if it's a condition, you need to add this rule to your parent, right? For any of the ones you're going down this way. But you also want to add the opposite of this one, so that when you're working on this rule right here, you can include the opposite of that in this one. I feel like I've explained that a lot of times, but again, that's what we're trying to do here, right? Is we're going to add our opposite to the previous, so that as we're going through, we know what we need to do. Then we just need to match our destination, right? If it's accept, boom, we found a position. We can just add that to our list of paths, right? We now know that we've found a valid path to get an accepted route. If it's rejected, now we know we're done with this tree, right? We know we can't go any further, so we can just stop where we're at. If it's a workflow, if our destination is a workflow, now we know, so this is the case where you're like right here, right? You now know you've reached some other point where it says, hey, I need you to go to another workflow to continue evaluation. So now what do? Is we need to just collect this up, and then we need to call our function recursively and have it evaluate all of its paths, right? and then we just add that to our list of paths, right? So that's what we're doing. We know we need to keep going further, so we're going to recursively call this on the new workflow name with our new parents list, and whatever that returns, we're going to extend our own path list with that, right? Okay, so if it's a fall through, we don't need to check. We aren't worried about a condition, right? There's no condition that would get you there except for your previous conditions, which you've already set up, right? So how do you check the fall through? Well, you just say, if it's an accept, I found a good path down the tree, so I can just add that to my list of paths. If it's a reject, I know I'm done. I can't do anything about it. If it's a workflow, I know I don't have to add anything for my own part, but I do have to go down that path now, right? It's some other workflow I need to go visit. So I'm going to do that and extend my paths by whatever it returns, right? I'm going to get some list from this. And so my list is, again, all the ones that I've accepted, plus all of these workflows where I've had to like traverse down further. And that is going to return. And then when I'm done, when I've evaluated all the rules, I just return that path. So it's a little bit hard to see because I have a lot of comments. I'm going to shrink it down just for a second. But if you take out all the comments, it's not that difficult, right? At any point, and this is what you just need to think about when you're trying to solve this, at any position in the tree, you're really just interested in the leaf nodes of it, right? And so those are the rules. And for each of those rules, you're really just interested in the opposite of the rules that you haven't that would evaluate defaults, the rule or the fall through that would cause you to evaluate true, and then you just add those to the list of your parents. And then once you've found an accepted one, you know that's one of your valid paths, and you put it down there on the list, right? So I think if you remove these comments, it's actually not that much code, right? But again, at a very high level, one last time, you're just kind of building up these paths, right? Oh, I know if I go down this path, it will get me to accepted. And I know, and based on that, I can do some math to figure out what parts would be in this accepted group, right? And I can do the same thing right here. I know that this part and the opposite of this part and this part itself will get you to a list of accepted parts. So what do I do? Now I have a list of conditions, right? I have a list of conditions and down all the accepted paths. Basically, I've traversed the whole tree and found all of these accepted paths. So then the question is, well, how do I calculate the size of that path, right? And that's this function right here. Hopefully it's okay for you guys to see. How do I calculate a possible combination for a single path? Again, the logic here is a little bit like we talked about right here. What we're interested in is, right, is we've collected all these values, and based on these values, or based on these conditions, I should say, we've collected all these conditions. And based on these conditions, we can sort of like whittle down the min and the max of each of the values, right? And so that's what we want to do here. So we're going to start with our min and our max values. You can think about this as the minimum viable part, and this is the maximum viable part that would take you down that accepted path. And then we just loop through the conditions and ask ourselves, how does that change our minimum or our maximum values, right? So we say, if the condition is less than, then that would alter the max value of it, right? So you can think about if the condition was x less than 1,000, we now know that x can't be greater than 1,000, right? Or greater than or equal to. And so we just set that x part to smaller, right? So now the max x is 1,000. And we do the same thing for each of those conditions, right? Another example, condition, let's do a greater than, condition greater than, right? If we know that S must be greater than 500, right? That was one of the conditions we got as we were going down the tree. We know that the min S value is not 1 anymore. It's got to be 501, right? It's got to be greater than 500. And so the new minimum value for S is 501. And that's all you're doing is you're just looping through those conditions and changing those values. The one caveat to that, and that's why you see me do a min or a max here, is obviously if you've already gone down the path, and I don't know if this actually happens in the tree, but it was something that came to my mind as I was doing it, is let's say that your S value right now is 1,000, meaning the minimum S value is 1,000. And you get to a condition that is where it says S has to be greater than 500. Am I saying that right? So your initial condition is S is less than 500 or greater than 500. And now you get one that says S has to be greater than, no, your initial condition, okay, I'm going to say it one more time. Strike that, reverse it. Your initial S, where you're currently at, your min S is currently 1,000. And you get a condition that says that S needs to be greater than 500. Well, you don't actually want to overwrite the 1,000 with a 500, right? You've already moved S way past 500, and you don't want to like change that. And so that's why you use these min max values, right? So we're going to get the current value and pick the maximum of those two values, right? So in this case, it would see, oh, S is already 1,000. I don't need to change it to 500. And that's essentially what this function does, okay? So again, just at a high level, you have some minimum part number and a maximum part number, and you're slowly going to start whittling down the max values or whittling up the min values based on the conditions that are in your tree, right? So we did this when we first started. If S is less than 1350, we can set that, if you consider this the max and this the min, we know we can set S to 1351. It's actually 1350 in this case, right, is what we set it to. If you look, I do a -1 here. But we're just going to do that for each of the conditions in our tree. So we're going to move down the tree and whittle down these two numbers for each of our conditions. So eventually then you've gone through the whole list, all of the conditions, right? We're for looping through all the conditions. Eventually you now have the minimum viable part number and the maximum viable part number. And now you can just do the math, right? And that's just a multiplication problem, right? It's the Cartesian product of those four things, right? Which happens to just be the max part minus the min part plus 1. Remember, we're doing inclusive here. Times the max part and min part for each of the values, right? X, M, A, and S. And that's how you do part 2. So this whittles down your problem from trying to solve a quadrillion values to just building up this list of trees that you can use to whittle down your valid part range. And then you just add all these up, right? So if this one's 1 million and this one's 2 million, this one's 2 million, this one's 1 million, you add all those up, and now you know how many total parts are possible, right? So that's what we do right here. We generate our accepted paths, like I said earlier. So that's going to be all of the lists. I'll do it one more time. I'm sure you guys get tired of me doing this, but we're going to generate all of these lists that get us to each of these paths, right? And we're going to have a bunch of them. And then we're going to call calculate possible combinations on that to get the value, right? That's going to use these to whittle down the min and max values. And then from there, we should be able to get some number. And so what is the total number of accepted? It's just the sum of those things. And that's part 2. And so if we run it, oh, I didn't do a time on this, but if you run it, you can see it runs really fast. It runs in microseconds or milliseconds. So I mean, we can do it right now. 663 microseconds, right, on the actual input. So as opposed to, um, you know, evaluating literally this many. Again, I don't know what this number is. Hundreds, thousand, million, 206, 125 trillion, right? The answer, at least for me, for part two, is 125 trillion. Instead of doing part one 125 trillion times, we just did some tree analysis or we thought of the accept and reject as a tree, and from there we could like dig down to the tree and find the thing. And that's what this day was. So I had a lot of fun doing this. Again, I had to spend some time. Part one was just, I think anyone could get part one relatively easy, right? You just say to yourself, "Oh, I'm building a programming language for this part thing," right? And the way I implemented it was destinations, conditions, rules, and then you just find ways to evaluate all that stuff to get to like kind of do the if then else's for you, right? I think anyone could get there pretty easy. The part two, which was fun for me, is, and this will happen a lot, is you'll have to do some kind of analysis of the input. There was one that I was working on a couple weeks ago from a previous year. I think it was called ALU. It had like a bunch of like machine code style instructions that you had to do. And it took me forever because part one was just, can you implement, the quote unquote computer, the ALU. But part two was, hey, can you, now you need to do it over, again, some huge, large space that makes it unfeasible. And you had to do some analysis. And it was really hard. I needed hints and I needed help to like figure things out because you had to like do some analysis on the actual input, right? And that's what this one is asking you to do here. At least for me, the way that I got to it was drew it out, think about it as a tree of like branching, and then kind of say, hey, you know what, I can act, how would I get to A if I was some part? And that was like the key thing that led me to be like, oh, do you know what, it's this list right here. And so if I can do some evaluation on that list to get me to that thing, um, that that will give me a solution without having to calculate all the parts. So there you go, day 19. It was a lot of fun for me. I enjoyed doing it. I hope you guys had fun. Hopefully my analysis didn't bore you to death. Again, this was another long one. I don't know, maybe I like to just kind of spit stuff out after I solve it and think about it. I can try and tighten that up a little bit, but I really do enjoy talking about this and going over it, because they're kind of fun to solve and it's fun to figure out. And I hope I would be interested. Did you find another way to solve part two? I think another way, in previous times, some of the solutions were to like track the min and max parts. And so like each of these would cause like a quote unquote split. And so you'd go from one set of parts to now two or three sets of parts that fit this. And then you just keep doing that down to eventually get to a bunch of sets down here. And then you could potentially like add those sets together to get the total. So if you did something like that, I would love to see it. But here was my solution. And I think, again, it's a lot of code and there's some little complexities. I could definitely clean it up a little bit. But I do feel like this one, at least for me, was much more easy to reason about. Oh, I was doing that all on the screen. You didn't see any of the stuff that I was doing, huh? Sorry. Anyway, I don't know how. I must have clicked that on accident. My point was, some of the previous ones, what they would have you do is, or some of the ways you solve it is you split it into pieces. So once you get down, the way that you do this is you say, now you create a section of blocks that are this, or parts that are this, and a section of parts that meet this criteria, and then you just recursively do that down for all the parts. So you're tracking a whole bunch of like part chunks, I guess is the way to think about it, and each thing is continually breaking them up, and then you can sum them up. But again, it was much more easy for me to think about this as a tree, right? That got me to what I that reasoning again. When I thought about that, I could break this into simpler parts, right? And that a lot of times is what helps me solve the problem, is, or just any problem in programming. Can I take a piece of a problem that I know I can figure out and just kind of build on those things? And so treating this as a tree really helped me do that. So there you go. Hopefully you guys enjoyed this. I'd love your feedback, especially the program. If I missed anything, let me know. Otherwise, we will talk to you tomorrow for day 20. Good luck, everybody.